My name is Pranav Managapati, and this is my Physics 2211 Oscillation Lab report. So the goals of this lab were to observe an object attached to a spring oscillating and use Tracker to create an experimental model for this object's motion. Next, we were supposed to create an accurate computer model of the object moving by using Newton's second law and the conservation of energy principle. Finally, we were supposed to compare the two models and explain any similarities and differences that we noticed. So the concepts explored in this lab are Newton's second law, which can be written as the net force equals the change in momentum divided by change in time. Then the force of the spring, which is force equals the spring constant times the displacement of the spring. And then finally net force, which is the net force equals the force of the spring, kx, plus the force of gravity. And then the energy principle, the three objects in this system are the mass, the spring, and the earth. And there's no surroundings, so the conservation of energy states that the change in energy should be equal to 0. And then no work means there's no energy change. So the formula for kinetic energy equals 1/2 mv squared. The formula for potential spring energy is 1/2 ks squared. And the formula for potential gravitational energy equals mg, and then the height. So the procedure was to record a video of the object moving in oscillation, upload the video to Tracker, create an experimental model for the motion, then create a computational model in GlowScript, and then compare the two models. So the experimental data can be seen here. This is the video that I uploaded to Tracker, and we tracked the points of the spring moving in oscillation. And this is the graph of the position and time in the x direction, and this is in the y direction, and these are all the data points collected from that. And then the experimental data can be shown here. So the initial position was negative 0.002 meters in the x direction and negative 0.702 meters in the y direction. And the initial velocity was 0 because the object was at rest. And the mass of the weight was 0.402 kilograms. And then the period of oscillation was 8.072 minus 1.994 divided by 4. So the period was 1.52 seconds. And the gravitational force in this case, which is F equals mg, was 0.402 kilograms times, gravity is only in the y direction, the acceleration only in the y direction, so in vector form it's this. And then to find the spring constant, we use the formula that the period of oscillation equals 2 pi square root m over k, and since we know everything but k, we can plug in our numbers and we get that the spring constant is 6.87. And then now we can find the initial length of the spring by using this formula, since the force of gravity is equal to the force of the spring. And we have everything here except the initial length, so once we plug in all the values, we get that the initial length was 0.127 meters. And this is our computational model in GlowScript. So the code is the initial mass of the ball is 0.402 kilograms. This is the initial position and initial velocity, and then this is delta t, and then the acceleration due to gravity is 9.8, and the spring constant we calculated, and the initial length we calculated is this. And then, so as you can see here, before my final time, kinetic energy initial should be equal to kinetic energy final. Gravitational energy should be equal to gravitational energy, spring energy should be equal to spring energy, and then initial energy total should be equal to initial energy final. And this is the force of gravity, force of the spring, the net force, and then this is the changing velocity of the ball and changing position of the ball. And then, so as you can see down here, this is calculating the change in kinetic energy, changing potential energy, change in spring energy, and the change in delta E, which should be 0. So from this GlowScript model, we got these three graphs. This is the position versus time graph for x, position versus time graph for y, and the change in energy versus time graph. So as you can see, there is a bit of discrepancy between the model and experimental in both of these, and this can be explained due to the force of drag, which is not accounted for in the computer model, but exists in real life. So what does it mean? Is the energy principle satisfied? And as you can see from this graph, the energy principle is satisfied, and this is because the change in energy is 0, which is what the principle states it will be. Since there's no external forces being implemented, it's only the system in context here. And then using the data we obtained, make two separate oscillation period, and estimate the period of oscillation from the x and y. So this is the oscillation period from the y data and this from the x data. And once again, the difference in period can be accustomed to drag, and this would make a difference in our calculation for the spring constant, since we use this period value in that calculation.